Okay, welcome to your second chemistry tutorial. Where we left you off in the last tutorial was here we were discussing the atomic radius and how it varies across the period. The example we took was of the first period, hydrogen and helium, and as we established, radius of helium is lesser because of the increasing nuclear charge, which in turn is because it has 2 electrons and 2 protons as opposed to hydrogen's 1 electron, 1 proton. Um, so with that we can see that in any period, as we go towards the right, as we increase the atomic number, the radius will always decrease. Now we're just going to look at the case what happens when we go down a group. So for that you can take the example of hydrogen, which is already here. I'm just going to let this be. So 1 electron over here, and we can look at the last element in this first group. This is hydrogen's group, of course, the first group. The last one is francium. Now francium has 7 shells, 7 in its atomic number is 87, which is huge. So it has 87 electrons, 87 protons. Now obviously you can imagine that those 87 will have a much larger force of attraction than this. However, what you also need to remember is that it has 7 shells. Let me just write that. 7 shells, while hydrogen has just the 1 shell. As you keep adding shells, you go down the group, you add shells. What you need to realize is, yes, the force that the nucleus exerts in to bring the electrons closer to it, it will increase, but that is not enough to oppose the increasing size, which is due to the increasing shells. The effect of the increasing shells will be much more than the electrostatic force, and this will be true for any of these periods. You can see it'll be true for this one as well, fluorine and iodine, for example. Iodine will have the larger atomic radius. So from this discussion we can see that across a period, atomic radius decreases, and down a group it increases. So on this topic you're going to be asked very basic questions. Maybe you'll be given a group with elements being, say, X and Y, and you'll be told to answer which one of the following has the smaller radius, or they'll give you a specific period and they'll tell you to arrange them in increasing or decreasing order. So basically you need to know this: when you go across the period what happens, and when you go down the group what happens. As long as you know that and you know the logic behind it, you'll be fine. Okay, that's it for atomic radius. I'm just gonna rub this out. Next physical property, it's a pretty important one: ionization potential. Uh, just to summarize what is ionization potential, I'm just going to draw an atom, sorry. Wait. Just take any, say this is sodium. Its configuration is 2, 8, 1. Now, as you know, 281, that means it has 11 electrons, and therefore it has 11 protons as well. So the charge, the electrostatic force between the two, you could say is 11 units. Each pair of 1 electron, 1 proton would count as 1 unit. And also, now you could take here's Na in the periodic table. If you go right across the period and you see chlorine over here, chlorine, again, 3 shells, but in the last shell it does not have just 1, it has 7. So I'm just going to draw that. There are 7 here and there is just 1 here. So of course over here, since there's 7, the charge over here will be 17. 17 units here and 11 units here. So if you consider any particle, any electron in the valence shell, that's the last shell. Okay, we'll draw one here as well. The force. Okay, so as you can see, I've drawn one electron over here, one electron over here. So as we established earlier, 11 units for Na. So this electron is getting pulled 11 units. Meanwhile, in chlorine, since it is 17 units, the force with which the electron gets pulled is much greater. So as a result, if you want to break this bond and free this electron, which means ionize this atom, what you have to do is supply energy to the atom. Okay, you have to supply energy and not release energy from the atom. And this is because in order to take this electron out of this shell, you need the energy to break this bond over here, and then also provide this electron some kinetic energy with which it will move. So to break this bond, the chlorine bond, to break the Na bond, it's quite obvious that the chlorine bond will take much more energy. So to take away an electron from chlorine will be much harder. It will require much more energy, say E1, and this energy, you can call it E2 over here. It's quite clear that E1 will be more than E2. And this is precisely the reason why sodium is a metal, chlorine is a non-metal, because metals always lose electrons easily. So you don't need much energy to take this one out over here. While over here, it's nearly impossible to bring this one electron away from this whole nucleus of 17. Okay, and also, if we draw a couple of more electrons in this chlorine atom, you can call this 1, this 2, this 3. Now say you remove electron number 1 first. Now this energy, you can call it E1. Let's remove this. Now once this is removed, you'll have just 6 electrons here. Now if you want to remove another electron, you could call the energy E2. If you want to further remove one more, you could call it E3 over here. Now in the first case, in this case, there are 17 protons hanging on to 17 electrons. In this, for E2, there are 17 E again, but there are only 16 E because you've removed the one. In this, there will be 15. So as you can see, the protons in E3, in this one, in E3, will be hanging on much tighter to the electrons. In E2, it'll be a bit less, but still more than E1. So from this, you can conclude that if E1 is the first ionization potential, E2 is the second, and E3 is the third, then E1 is less than E2 is less than Okay, so in the next video we'll be again dealing with ionization potential, but this time we'll be studying how it varies down the group.